Okay, so I think without much ado, let me just hand over to Chen to tell us about entanglement routing.
Thank you, Ritu.
Yeah, right.
Hi, everyone. I'm Chen. I'm an associate professor in the Department of Computer Science and Engineering at the UC Santa Cruz. And today I'm very glad to talk about our recent work about the protocol design of entanglement routing for quantum networks. So let me briefly introduce my background. I'm actually a very networking guy. I did my PhD in UT Austin and working with Simon Lam. So some of you probably know him. He has already retired. He was very active back to 80s and 90s. Actually, he was a first TPC chair of SICOM back to 83. Then after graduating my PhD, I had 3 years with University of Kentucky as a faculty there, and then I moved to UC Santa Cruz. So I have worked and I'm working on different topics of computer networking. And the current focus are on quantum networks, of course. That's why I'm very excited here to talk about our recent work. And other projects, including programmable data plan, P4, those kind of stuff, network security, IoT, wireless networking. There are quite a few different projects because my students, they're interested in different topics. So I have to spend my interest in different topics. I don't want, well, my style is not pushing students to work on my projects, but let them explore their projects. So eventually they end up with different topics, but all those topics are related to computer networking. So why I started to work on quantum networks. Okay, so there was a long story, but let's just briefly talk about it. When I was an undergraduate student in China, that's back to 2005 and 2006, and I did an undergraduate project, bachelor's project about quantum computing and the programming languages for quantum computing. But I did that project very briefly, and well, we didn't, publish anything seriously, but I learned something, all right? But of course, after that, I switched my research to other networking problems. However, in 2019, I occasionally read a paper written by Nanjing, and Nanjing is my friend. He actually graduated with from a same high school as of mine, and he's of course a few years older than me, but well, he's a physicist, theoretical physicist at Chicago University, and very well-known expert in quantum communication. So I read a paper. I found the paper was very interesting. That was definitely a networking problem, but that papers and those and the other papers that paper cited, I read those papers. I find those paper were all talking about networking, and in fact a networking problem, but they solved those problem in a physicist aspect. Okay, so then I thought, well, how about let me try to work on those problems from the point of view of computer networking researchers. All right, so I started this project, and we published a paper on CCOM last year, and we're still working on the follow-up works. So let me first introduce some building blocks of quantum networks. The first concept is called quantum entanglement. Some of you have heard about quantum entanglement, and some of you probably have already known that because you have former discussions about quantum computing. Basically, a quantum entanglement is a state correlation of two particles, and we call those two particles qubits. So those two qubits are correlated. It's just like we have two electrons, and they have different spinning directions, right? And if we consider one direction is 1 and the other direction is 0, then these ones and zeros are the states. So we consider the quantum entanglement as two flipping coins, and they're correlated such that even if we have no results, okay, will be for those two coins. But if we can see results from one coin, then we can definitely infer the result from the other coin. So that means the state they are correlated. Okay, so if we see a 1, and we can infer the other is 1. Or there are another type of entanglement. If we see a 1, then we can infer the other is 0. Or if we see a 0, and we can infer the other is 1. Okay, so on and so forth. Even if those two qubits are separated by a large distance, we can still have this property. And this is called an entanglement. And the entanglement should be somehow, established using some physical, operations. So let's use this blue circle to denote the communication parties, Alice and Bob. Okay, and we use the red dots for the qubits, like the coins. Those two dots are qubits. So Alex and Bob, they can send photons from a quantum channel. And for example, the quantum channel can be optical fiber. And here is a dashed line over here. This is a channel. So a quantum entanglement can be established by sending a single photon from Alice to Bob, or from Bob to Alice. And of course, the success rate of this sending is not very high, but we can have multiple tries to improve it. All right. And then the entanglement can be established. And a very nice property is, and for example, there's a paper in CCOM 19 talk about the link layer of quantum networks. But that, of course, was just one example of the link layer. There are multiple link layers of quantum networks, but that work was one example. There are other works, okay? So, so a nice property of quantum entanglement is that if you know one of the qubit, the other one can be inferred, right? So that actually can provide a very, very secure communication channel. That is, if I have a secret, right? I encoded those secret in those qubits, and if the receiver sees one, okay, there's an operation called measurement. So if the receivers do a measurement on the received qubit, the receiver can know the result of the state, right? And of course, the sender also knows the result of the state, because the sender can also get the measurement result from, of the qubit. So, and this channel is quite secure because a property of a quantum entanglement is that if one of the qubit is kind of like measured, then the entanglement will collapse. It's so-called collapse, right? And in that way, if there is an eavesdropper on that channel, and those eavesdropper get the qubit, then both sides can have the knowledge that this channel is under eavesdropping, okay? So but of course, still a probability thing. So it's not guaranteed that the two communication party will know there's an eavesdropper. But you can somehow engineering it to be very high probability. All right. So in classic communication, we want authenticity and integrity. Of course, they are very important. And in a quantum entanglement communication setting, so if we want to send a data, we can just encode the data to the two qubits and send the qubits. Okay, and we can achieve the so-called perfect confidentiality. That is, the eavesdropper, any operations by an eavesdropper will be reviewed. Okay. So there are many applications of quantum entanglements. For example, one of the most one is called quantum key distribution, QKD. And there are others like distributed consensus. I spend some time, let me spend some time to talk about quantum key distribution in case you haven't heard of it. So we know that existing key distribution relies on the complexity of integer factorization, right? Because if for example, we want the two parties we want to communicate, and what do if we want to set up a key? We use RSA, right? And to authenticate with each other, we see the digital signatures of the certificates, verify it certificates, and then we send the session keys using RSA or Diffie-Hellman key exchange. Okay, so these are based on the integer factorization, and the security of this key distribution relies on the difficulty or hardness of integer factorization, right? We know that one day if integer factorization can be done in polynomial time, then the existing key distribution method may not be that secure. All right, so QKD does not rely on integer factorization. It uses quantum mechanics to detect the existence of or absence of an eavesdropper. So this is also a type of sensing, right? Sensor network. So if Eve attempts to learn the data value, right, it needs to measure the quantum states, and the measurement will cause the collapse of quantum state, and this collapsing will be reviewed to Alice and Bob. So so this is quantum mechanics that to achieve the security. So the three steps of building a security channel we know are: first, authentication, right? Second, key agreement. Third, encrypted data transfer. So of course, those three steps are implemented in today's TLS, SSL. And we know that the authentication is usually done by either the two parties has shared keys, or we use RSA, like today's certificates, right? Rely on RSA. And if those two parties share keys, and these shared key can only be decrypted by brute force, there's no better method to attack to the pre-shared key. But if that rely on RSA, then factorization is a method to attack. Okay, so key agreement usually either Diffie-Hellman or RSA, and those methods can be attacked by discrete logarithm or factorization. All right. So, and data encryption, it's either on one-time pad or AES, right? And they can be hacked by brute force. And AES has been considered sufficiently secure, so we don't have to always use one-time pad. And of course, one-time pad is the most secure one, but AES has been considered sufficiently secure. So what QKD does, QKD only solves the key agreement problem, okay? It has nothing to do with authentication. It has nothing to do with data encryption. Of course, you can use QKD for data encryption, but that's very expensive. That's very expensive. That means every bit you send is a data bit. That's expensive, right? So you always just want to send a key and use a key for encryption later. So today's method is RSA plus DH, Diffie-Hellman, plus AES. That is a standard of today's communication, secure communication. So, but we know that one day it's possible that the factorization and the logarithm will become possible in polynomial time. Why it could become possible? For example, quantum computer, right? Last time you talked about quantum computer. So quantum computer is able to make factorization in polynomial time. We know that. So it's possible that one day we have a sufficiently strong quantum computer, so RSA and Diffie-Hellman will be gone, okay? It's no longer secure. Then what we can do is we can replace RSA and Diffie-Hellman by pre-shared key and QKD. All right, that still preserve the security. And of course, that method will be dead if AES is broken one day. Okay, but we don't expect AES can be broken in near future. And if that is the case, then people may rely on a key, pre-shared key plus QKD plus OTP, one-time pad. All right. So the problem, so the benefit of QKD is that so the exact benefit of QKD is that is this gap important to the security applications? Okay, I know a lot of people they want to promote quantum communication and quantum computing, right? So they claim that QKD is really, really important and it could be the standard of the future secure communication, but I'm not in that opinion. What I'm thinking is that QKD could be important, but it's really depending on whether we are interested in this gap, okay? If that gap is important, then QKD is important. If that gap can be solved with other method, then QKD may not be that important as claimed by someone. All right. Okay, so and another application domain for QKD is that we know that many communications are real time, and those and many communications are so-called retroactive. All right. So what does a retroactive mean? So retroactive means if the attacker cannot decode or decrypt your current communication, but it's just like stores your old communication, okay? And hopefully one day they can decrypt it. And that still could be a very strong and successful attack. For example, the content of diplomatic cables. Or this could be could have the retroactive vulnerability. All right. So QKD is also useful if we want to protect this retroactive vulnerability by replacing RSA and Diffie-Hellman, because no one knows RSA and Diffie-Hellman could be broken one day, right? So QKD can be a method to protect it. And also there's another limit of QKD is that, as I said, if we use, yes, Annette, is there a question? All right. If we use RSA, right, like today's authentication, then basically any public client can visit a web server and by authenticating with and the authentication can be done by RSA, right? This is called open communication. That is, anyone on the internet can join the communication. All right, just like the current internet. However, in QKD, since we assume RSA is not secure, we can rely on RSA to perform the authentication. So that then we have to rely on the pre-shared keys. So if that is a pre-shared keys, that means only a closed group of communication parties can hold those keys. And for other new members, they need to have an offline method to get the keys, right? So those keys are used for authentication, and key agreement will be done by QKD, of course. So QKD can only work for this closed communication rather than the open communication. So this is another limitation of QKD. All right. So there are two main types of networks that can support QKD. One is called prepare and measure network. So in a prepare and measure network, basically just a sender or a third party prepare a qubit and send those qubits to the receiver, and the receiver will measure the qubit. And any eavesdropper who is on the channel could be detected by the sender or the receiver. And this is called BB84 protocol, okay? Developed quite a few, like 30 years ago. And a limit of that is the distance of transmitting the qubit is limited. So another type is called entanglement networks, all right? And the earliest protocol for this type is called E91, and E91 allows a sender like Alice or a third party to generate an entanglement pair, and the entanglement pair will allow each of Alice and Bob to get one photon, and then based on some other operations, eventually Alice and Bob can get the shared secret. So this is E91 protocol. So one example, if we want to extend the distance, communication distance of the Alice and Bob, because, well, I think I didn't say that. If Alice and Bob are very far away, right? Very, very far away, the success rate of generating an entanglement between Alice and Bob will decrease exponentially with the distance.
Chen, could you give us a sense of distances you're talking about here? Like what is very far and what's possible?
I think it's depending on the hardware, right? And nowadays it's possible to make an entanglement, I think, within several miles, and I think someone in China even can make entanglement with satellites. But that's really depending on the hardware. Of course, you want to make a longer entanglement, the success rate will decrease. So you have to increase the number of attempts in order to make a successful one. And their experimental results may be after a big number of attempts, they can get a entanglement. Okay, so you can consider that several miles would be a reasonable distance to generate a successful entanglement. Okay, so what if we want to communicate with longer distance? One solution is, of course, like today's network, we add routers between the source and destination, and those routers are called repeaters in quantum networks. And this is very similar to classic store and forward networks, that every repeater or every device will generate a entanglement with its neighbors, and they will the repeaters will get the secret data, right? And the repeater will send the secret data to next hop and all the way up to Bob. So each pair of adjacent nodes will use QKD to exchange the encryption keys, like the AES keys. However, a limit is that, well, if you assume all repeaters are secure, then it's fine, right? But what if in future we have a very large network like internet to connect many users, and there are a lot of repeaters? Can the user trust all the repeaters? It may not be possible. And if we assume all repeaters has been trusted, then it's of course increase the vulnerability of the whole network, because as long as the attacker can hack one of the repeaters, it can get a lot of information. So this method is secure only if the repeaters are secure. And another one is more popular solution is for untrusted repeaters. That means the repeaters will not know the secure information, like the key.
What are these repeaters doing? Are they going all the way digital to bits, or are they operating at lower layers? Or?
If you mean the trusted repeaters, they will all the way go from the qubits to actual data.
I see.
Okay, but untrusted repeaters are not doing in this way. The untrusted repeaters will use entanglement swapping. This is a physical operation to achieve end-to-end delivery. And I will talk about it later. So the applications other than QKD includes distributed quantum computing, distributed coin flipping, that is to make a randomness, right? And leader election and Byzantine agreement. All of them are kind of very hard, and also time synchronization. All of them seems to be very hard on distributed system or very classic distributed system problems. But with quantum networks, those problems can be perfectly solved, or in a way or another. All right. So a more exciting future compared to QKD is that what if we can have distributed quantum computing? That is, nowadays we know that quantum computing is usually done by one server, right? That runs a number of bits, right? But if we can connect remote servers, remote quantum computers together, then we can significantly increase the number of bits that a quantum computing can utilize for a job. That can increase the capacity of quantum computing with the help of quantum networks. So these applications are also very exciting compared to QKD, because QKD is one of the example that people always mention along with quantum networks. But I do think the benefit of quantum networks would go beyond QKD, and I think I've already talked about some limitations of QKD. Right? It's definitely not a ultimate solution for every problem. All right. So this is a picture that talks about the future of the quantum networks, and eventually we would like to go from the trusted repeater network all the way to the quantum computing network, which means all quantum computers can connect it, okay? And those quantum memories can be shared in remote distance. Okay, so, but that's future. So how do untrusted repeaters to deliver the entanglement? So we know that the success rate of the two communication parties will decrease exponentially with channel distance. So it's always possible to add parallel channels, like you have more entanglements, right? That of course increase the success rate linearly. But as we know that the success rate will decrease exponentially, then there's a A better solution is we add the relays, and these are so-called untrusted repeaters. And the workflow of untrusted repeaters can be done in this way. First, Alice and the repeater generate a entanglement, and repeater generate their entanglement with Bob. But Alice haven't put any data into it, so the secret information is not known. And the repeater perform a action called Bell state measurement, BSM, and the result of the Bell state measurement you can consider, okay, in our networking engineering perspective, you can consider it place a internal link between two local qubits on the repeater. All right, and the result would be Alice and Bob eventually will have a shared entanglement with the help of the repeater. And this operation can be extended to multi-hops. So if we have multiple repeaters on the way, of course, this is an example of two-hop entanglement, and we can extend it to n-hop entanglement. All right, but remember, the success of generating a repeater between Alice and Bob, a repeater and Bob, and even the internal link within the repeater, they are all probability based. Okay, they are not guaranteed. So every attempt could fail, and they fail in a probability depending on the hardware you're using. Okay, so the entanglement also decay very fast, usually a few seconds to up to 1 minute. The entanglement will be gone, and the current well, I don't know if that is the current standard, but from the literatures I read, many people will just use the synchronized communication model to perform quantum entanglement. That means every round of entanglement and BSM and all those swapping, we call this BSM, okay, we may also call it swapping, can be done in a time slot, okay? And each time slot includes 4 phases. And this is my, I summarized this kind of 4 phase from the literatures I read, okay? And within each time slot, there will be some resource contention because every node has a limited number of qubits. And also the time is limited, and also the some communication channel could be limited, like the fibers. They can be only have a limited number of fibers, of cables. I mean, for example, the number of qubits, okay, or the number of quantum channels from one node to the neighbors. They can have a contention. So they are limited, and second, they should be allocated exclusively for one sender and the receiver. That means one Alice and one Bob. They should be allocated to them. They cannot be shared by multiple users.
Let's consider
so here is a video about the networking model. The video is recorded by my student. I think you can hear the voice, right?
And thus, it has classical and quantum processing power at the same time. All nodes have access to the internet and can communicate with each other on the classical computer part, with potential confidentiality flaws. And we assume the integrity of the classical communication. We use the dashed line to denote a quantum channel. The nodes are connected with the quantum channels to form the quantum part of the network. You may notice that more than one channels may present among the same pair of nodes, and hence, multiple entanglements may be established simultaneously. To establish a local entanglement, each end of the channel should be assigned with a qubit, as the legend shows, and the local entanglement is shown as a solid line between the qubits. The quantum processing power of a node is determined by the number of qubits it holds in the quantum computer. For example, 3 qubits in the node 9, it can simultaneously establish 3 entanglements with its neighbors. As there are more than 3 channels connecting the outside, the qubits are properly assigned up to 3 channels, 1 qubit per channel. As a pair of neighbors may share multiple parallel channels, like node 7 and node 9, multiple pairs of qubits can be assigned to the parallel channels. Let's move on to the communication model by following the workflow of a single time slot with 4 phases. In phase 1, from pure classical communication, each node is informed of a list of the node pairs to build a multi-hop entanglement. In this example, a single pair, node 3 and node 11. In phase 2, each node exclusively assigns its qubits to quantum channels connecting it. This assignment is based on a consistent path selection across different nodes. For example, the highlight 2 paths are selected. Then, the qubits assigned to the channels to fulfill the path. After the assignment, each node tries entanglements on the selected channels until a success or timeout. In phase 3, each node knows the entanglement results and exchanges this information within K-hop, such that each node has a K-hop view of the entanglement successfulness for the selected channels. We call this K-hop link state. In this example, the channels 3, 7, and 9, 12 fail, while 3, 9, 9, 7, 7, 11 succeed. The parameter K is determined by the classical network speed and the entanglement decay time. Typically, 3 is enough according to our experiments. Finally, in phase 4, each node do the Bell state measurement based on its K-hop link states, like the both solid lines shown in node 7 and node 9. Then, the measurement results are sent to the node 3 and node 11 to help them adjust their qubits for the remote entanglement.
Okay, so in this way, after a one-time slot, the node 3 and node 11 can share an entanglement, a pair of entanglement, because there's a path actually from 11 to 3, and the path is connected by the quantum link and of course the internal link. So this is a network problem we modeled from the physics knowledge information. So this is the building the multi-hop entanglement is basically a problem of routing in the quantum networks. And of course, for every time slot, we may have multiple source and destinations. And for every source and destination, we want to maximize the number of entanglement they can share or number of qubits they can eventually deliver. And with the time and resource limitations. So we summarize some difference compared to classic networks. For example, the packets are not, there's no packets here. So this is definitely not packet switching because no packet can be retransmitted. There's no retransmission. And the assignments from qubit to channel and qubit to BSM are fixed actually. And there are two types of link states. Usually when we talk about computer networks, right? Link state is either dynamic or static. But here, there are one static network topology that is the nodes, the channels, the qubits, but there's also some dynamics that is the entanglement result after phase 2. Okay, we make an entanglement, right, for every neighbor, but it doesn't guarantee you success. So this is probabilistic. So that's very different from our current networks. And also the routing metric is not additive. We know that in current networks, most routing metrics are additive. For example, hop count, right, latency, they are additive. But here, definitely the routing metric is not additive, and we will talk about it later. So why is it not additive? So let's consider these two examples. We understand from Alice and Bob, A and B, right? And here is an example network that we have one pass ACDB and another pass AC prime D prime B. All right, and we have another example. We have those two parallel paths that C and D, they are actually one node, one untrusted repeater, but still A and C share two quantum channels, and D and B share two quantum channels. So which one is more reliable? Which one is more reliable? That means once you want to build a quantum path, do you want to spread it out like we do traffic engineering, right? We want to spread the flow across different paths. Or do you want to put all flows on a same path? The idea is actually we prefer the second option, that we want to have more parallel paths as possible. Look at the first, the top graph, that if we have this link failed, AC fails, and AC prime fails, and CD fails, then the network will fail, right? This round, we cannot deliver anything. However, in this way, even if we have 3 quantum channels that are unsuccessful, we are still able to make one successful entanglement, okay? So that means the second option is more reliable than the first option, right? So from this idea, we always prefer the wide and path, and the path with fewer hops. Of course, fewer hops we understand, but the path with more parallel channels is another metric we should add to this routing. So like here, we make a definition. We define a 2-3 path, means the path has 3 hops, and each hop has at least 2 parallel channels. So that means this is a 2-3 path. And the metric to evaluate this wide and shorter hops is non-additive. Okay, so the details can be found from our paper. So and existing algorithms like the packet switching ones, the multi-hop wireless ones, and the circuit switching ones, or SDN routing, none of them can work on this networking model. So we should be able to design a new algorithms. But I don't want to put too much time on the algorithms, because I think most of you are experts on networking protocols and algorithms. So if you are given the model, then the remaining would be just, standard the algorithms analysis and design and heuristics, right? So we designed 2 algorithms. One is called Qpass, and the other is Qcast. Qpass use offline routing and segment-based path repair, and Qcast use online routing, and it use another method to repair some of the paths. So I will talk a little about Qcast. So in Qcast, it's contention-free. That is, if we build the path for 2 source and destination pairs, we don't want them to share any qubit or channel. So this is contention-free. All right. So if we want to build one path ACB, and we want to build another path ADEB, so that's 2 paths. Then we will in the each time slot, A will build the entanglement with D, and A will build entanglement with C, and C will build with B, and so on and so forth. This information will be broadcast to every node using the classic internet. Then they will start. But of course, there are some remaining resource, okay? And those remaining resources may not be used. They just make it like free over there. And we designed a so-called extend Dijkstra algorithms, which is a Dijkstra algorithm, the version of Dijkstra algorithm that supports non-additive metric, okay? So that includes the recursions. We know that a standard Dijkstra algorithm, the metric must be additive, otherwise we can't prove its correctness. But now we can prove the correctness, but we will make a Dijkstra algorithm as a recursive algorithm. And this time complexity is at least for now, I think that's definitely more complex than original Dijkstra algorithm, but we haven't had a very careful analysis. But at least for a several hundred node network, the time complexity would be fine. Just a few, less than 1 second, okay, for the extended Dijkstra algorithm. That works for monotonic, but a non-additive metric. Monotonic, of course, means if we have one hop longer, then the path basically get worse, so that the routing cost will increase. So this is called a monotonic routing cost, or routing metric. All right. That's very obvious, because if we want to generate a entanglement between A and C and comparing generating another entanglement between A and B, of course, the former is easier compared to the latter. Okay, the Qcast works first. We identify the source and destination pairs. In this example, we have 2 pairs of source and destinations, right? And then we will select the path using the extended Dijkstra algorithm, okay, to get the best path for each pair. And then we will pick the remaining, we'll pick the best of the best paths, and we will also make the remaining path to act as some, backups, or you could consider it as redundancy. Okay, so this example, we will put another path between 4 and 14, that is 4, 10, 14. Okay, so we will do multiple paths for every pair of nodes, because we know that no path is guaranteed to succeed. So if there's any link failure or unsuccessful entanglement, that means unsuccessful link, we need something else to recover. Okay, so we will make the network resource as more as possible to build, possible entanglements in case those entanglements can help the source and destinations. So in P3, phase 3, every node will know its local link state, that whether the local entanglement is succeeds or not. It could be successful, it could be unsuccessful, right? So for these red ones are unsuccessful links, but the others are successful links. Then a node may share the information to k-hop neighbors, and they can be as low as 1 and can be as high as infinity. So in phase 4, every node will determine which internal link should it place, that which Bell state measurement it needs to be done to help the source and destination. Okay, so this is the eventual result. So eventually we will see that 4 and 14 has 2 successful entanglement. One is from 4, 6, 14, and the other is from 4, 5, 7, 8, 14. Although the 4, 5, 6, 7, 8, 14 is not the best path we select at the beginning, but it actually recovers some failures, for example, between 5 and 8. Okay, so so this entanglement helps to recover the path. All right, so we have a quite complicated recovery algorithm to determine which path can be recovered. I would just skip it because we don't have too much time here. And if you are interested in the details, you can refer to our original paper. So we built a simulator to evaluate the performance compared to other algorithms that I've read, okay, from other researchers. Most of them are from physical physicists, some of them from theoretical computer scientists. So the evaluation will focus on the throughput, which is the number of qubit we can deliver for each time slot. And we call it e-bit per second, number of entanglement bits per second, okay, number of e-bit per second. And we use a reference setting network with 100 nodes, and the probability of the entanglement is 0.6, and this is the probability of an internal link. And of course, those parameters can be changed. And the number of hops of the link state information is 3, and the M is the ED, I think, is the degree of every node, and M is the number of source and destination pairs. So we also have a visualization of the simulator. So here is a reference setting. We compare Qcast and Qpass with existing algorithms, and we find the throughput is improved quite a lot compared to previous work. And this is a CDF, and the x-axis is the throughput for different, we make the random source and destinations for every time slot. So, and then we plot the throughput. So the throughput is basically for Qcast is 4 e-bit better than Qpass, and they are much better than the other protocols. And if we increase the size of network, we still preserve the advantage. So we vary the network size, and we will see Qcast is always the highest, but of course the throughput will decrease, because when we make the network higher, bigger and bigger, right? That means the path could be longer and longer. So it's harder to make a entanglement successful. And here is the number of source and destination pairs in one time slot. Still, if we vary this value, then Qcast shows the best performance compared to the others. So here is whether we should apply the recovery method. So we compare those Qpass and Qcast with and without the recovery. And we see that with recovery, it can achieve 1 e-bit better compared to the version that without a recovery method. Okay, so let's conclude this work. We developed a quantum network model from the literatures, and we proposed 2 algorithms. And there could be, of course, better algorithms and better models. For example, if you want to beat our algorithm, that's very possible. Okay, because that's kind of considered an early work. And if we want to achieve fairness among different source and destinations, of course, that can be as another direction we work on, right? And there are some others like QoS. And you can try this simulator. And if you have problems, you can give me emails. And thanks. And I'm happy to take questions.
Thank you, Chen.
And I'm currently trying to, do some implementation with a physicist, try to use their hardware. So, of course, when we deal with hardware, the original network model may not always be realistic, right, as you can imagine. So we're still working on it. And if you want more ideas, I think our work just serves as a bridge between the physicist and the computer network scientists. So and I hope we can motivate more network researchers to start working in this area.
Yeah, absolutely. Can we get access to the hardware too, or what is?
No, they haven't successfully built it yet. So I'm collaborating with Texas University, Texas at Dallas, and William Mary College. So these physicists, they are building their quantum hardware, but so their ambition is to build a quantum LAN, QLAN. So, and those QLAN, eventually they plan to make it accessible from public, like those cloud lab, right? So,
Yeah.
and I don't know how many years we will go from their current progress to eventually make it public available. But still, it's nice that we have some effort on this direction.
Yeah, sounds exciting.
Yeah.
Thanks for taking the time and telling us about this stuff.